I want to make a thing that I think I've used more than any other thing in my maths teaching to students, because it's all about how things move and the way things move and the rate at which things move. I'm talking about differentiation. I'm talking about calculus, which is the mathematics of things that change, which, to be honest, is the mathematics of most interesting things, because things that don't change are fundamentally boring. In the applied world anyway. It's strange that in school a lot of students think calculus is a very pure bit of maths, when actually it's almost the most applied bit of maths, but that's because school maths doesn't really feel like maths in the real world, but let alone maths at university level. However, in the UK, students study calculus age 17, 18, unless they're doing the IGCSE course or an additional maths course when they might meet differentiation a bit earlier, but it's kind of mostly towards the tail end of their school career. And it is a really important piece of mathematics that's, thanks Isaac Newton and Leibniz. The uses of calculus are far and wide. Unfortunately, when you first meet it, it's quite often done in this kind of learn this algebraic technique way rather than in being used. I'm not claiming that all maths has to be useful. I'm just saying that calculus is definitely useful, as well as being beautiful. Preaching aside, the nice thing about GeoGebra or dynamic geometry in general is that it makes things move, and when you're going to study calculus, it's all about the way or the rate at which things move or change, and so it's an obvious thing to do. So let's build a simple demonstration of what I'm going to call the gradient function, which I know that most people watching this will understand to be differentiation, but my point is you could build this file without even calling it differentiation and it would still be understandable, even if you build it live. Let's get started. Here's a GeoGebra window, GeoGebra Classic 5 as usual. You could do this in any of the others as well. And although GeoGebra will actually analytically differentiate stuff, I'm not going to do that. I'm going to do it visually with a function. So let's pick a function. I'm going to call f of x. And I quite often pick the same function to work with here. I'm going to use x squared and then 1 minus x. I'm actually going to add a bit to it. So if I zoom in on this, you can see I'm using this function because it has 2 turning points. 2's maybe better than 1 to talk about this, and it's got down bits and up bits, by which I mean decreasing and increasing bits, and that's useful, and it's not necessarily hitting the axis at confusing points. Anyway, any function will work, and I want to talk about the gradient of this function, which is its slope. And the first thing to realize is that it's not a straight line, so the gradient is not the same, and this is the first hurdle for school students, is that they're used to doing slopes of straight lines, which when they get the hang of is relatively obvious, but when you're doing slopes of curves, it's not obvious because there's no straight line. So what we need to do is define what a gradient of a function is, and if I put a point on the function by using the point tool, I could have used the point command. This drags around, and at different points on the curve, there will be different gradients or slopes, but it's not obvious what those slopes should be because none of these bits are straight until you realize that you could use the tangent to the curve at that point. Now, we could build the tangent to the curve, and actually we're doing differentiation from first principles then, but let's do that later. Let's first of all just realize that GeoGebra has a tangent command. There it is. If you don't know how to use a button, then hover over it, select point, then function. There are some other options there, but hey, select the point and then the function, and it will build the tangent. Already, moving this around is a really helpful way to have a discussion with a bunch of learners about what gradients of curved functions are. And they change, and that's the point. And tracking them over time is the idea of the gradient function. Not necessarily over time, but as x changes, the gradient changes. So what does the graph of the gradient at any point look like? Hey, that's the gradient function. How do we plot it? Well, it's actually pretty easy. First thing, before we do that, it might be worth mentioning that just if you don't want to drag it around, you could right-click and turn the animation on, and we'd have a moving thing. And GeoGebra is relatively sensible about the way it animates points on functions. It doesn't go off to infinity off here. It just takes the x values roughly that are visible on screen and uses them. And already I think a nice exercise with the class would be to get them to realize when is the gradient positive and negative. Down if it's negative, and up if it's positive. So it's negative or 0, positive, 0, negative. Getting a whole class to do this with their arms, however childish it seems, is a nice physical way of getting some intuition for what slopes of and gradients of curves mean. And to be honest, that's what a gradient function is doing. It's just tracking what is the value of the gradient, and at least negative and positive is an easy thing to see. So let's actually track it. What I would like to do is measure the slope of this line. Now, we could build a triangle and measure its slope, but there is a slope tool. It's buried in here. You could use the command slope. If I start typing it, you can see it wants a line, and the tool just wants the line. So instead of, well, I could stop the animation and click on it, or I could just click on the line there. And you can see, although A is off my screen at the moment, that it has drawn a triangle. And it's drawn a triangle of width 1 and height gradient. And this is kind of the definition of a gradient triangle. And you may or may not like having that there. You could just hide it if you want to hide it. But there's still an m value in the Geogebra memory now, which is the slope of that line. And it does change as a moves around. If I let it animate, you can see that's moving and changing. It's negative. And if I turn on the gradient triangle, you'll see it'll come back on the screen here. Very negative. 0 there, positive, 0, negative. So that's visualizing the gradient for us. And what I'd like to do is track that as the x value changes. And that's not actually that hard. It's almost one of those things that's so obvious that it's not obvious. So I just want to draw a new point on the screen. And the way to write a point is coordinate brackets, parentheses, whatever. The x coordinate I'd like to be the same as the x coordinate of the a point. So I'm going to use x of a, x brackets a there. And that describes the x coordinate of that point. So the same x coordinate, and the y coordinate, instead of the value of the function, I would like the gradient, which I've measured just now as m. And it'll also make a new point, and it's going to call it b, and there it is. It is suspiciously in the shape of a quadratic, which may not be a surprise if you know anything about how cubics and gradient functions work. Really though, that b disappeared. I'd like to leave it a trace of it, so let's just right click on b and turn the trace on, and now when it appears on the screen it will leave a little line behind it, the trace of b. In fact, there it is, and it does look like a quadratic. Trouble is, when I zoom in, like any traces or move the screen around, the trace disappears. So worth mentioning, and let's just pause this for now, there's always a more permanent way to leave a trace, and that's with the locus command. A locus tracks a point as another point controls it, or a slider controls it. And you can see to do that, you select the locus point, then a point on an object or a slider. So I'm going to select point B, and the one that controls it is A as that moves around, and it's going to draw the path of B as A moves. And that is the thing that was tracing out. And now when I zoom in and out, it doesn't disappear. In fact, when I change the original function, let's just put a 2 in there, the gradient function is changing with it. So no differentiation has been mentioned in this, but we have plotted the gradient function as a track of the gradient as A moves around. And it's just really nice to see that happening as it moves around. I might change this back to my original function again. You could put a slider in here and watch it change dynamically. So far, so good. We could do some prettification. We could add some buttons to turn on the trace and the locus, and maybe we'll do the aesthetic job of this now. But the point is, once we build this thing, we can change that original function and see what's going on. So maybe when we've done some aesthetic tidying up, we can just put some other functions in here and demonstrate how you might use this file in the classroom. I really think building this file live in front of a class has quite a lot of value. There is merit in ready prepared files. I'm the first to do that, and my whole series here is about making a file and spending a lot of time doing it. But building something from scratch in front of someone, maybe as these videos do, teaches you quite a lot about the thing. And that's quite a nice thing to demonstrate to students, particularly if then you give them the option of going to build the file themselves. As I quite often say in these videos, quote from Richard Feynman, if he said, if I can't, what was it? What I cannot create, I do not understand. And I kind of internalize that as, if I can't build it, I don't really understand it enough. And if I can't build it in GeoGebra in mathematics, I don't really understand it. If you can build a file like this to demonstrate the gradient function, you really probably have understood the basics of the gradient function. And so if they can go and do that, they will get a kick out of it and they'll understand it. But let's do some aesthetics. I think I want some hide show options to make sure things can disappear. So I'll use the checkbox in its traditional way now, rather than doing anything clever with it. Let's do this is a checkbox. So when it's ticked, I want things to be visible. So I'll have it ticked for show tangent. And I can just do loads of things with this. I can show the tangent and just click on that and it will put the tangent in there. And maybe I'll also say show tangent and slope. I could do a separate tick box, but let's have the slope there. You can even click on that triangle there. And now I've got a checkbox that will hide and show those things. Let's do a couple more for the show gradient function. Maybe I'll do point and function. And we'll hide and show B. And you can choose whether you're going to show or hide these things. So this is me using the checkbox in the sort of toolbox graphical user interface version of GeoGebra. If you want to go and change how these checkboxes work, it's slightly irritating. I didn't tell it to show B. Oh no, it's just tracing B, that's right. So actually I need another checkbox to turn the trace on or off. I might want to trace the point B, and that's less obvious how to do it. When you click, having a little moment here. GeoGebra, are you with me? Yeah, checkbox, click on the screen. I'm going to do trace B, and this time I can't click on something to tell it how to use that. So I'm just going to say, let's make a checkbox. It doesn't do anything at the moment. But if I then look up a command, I think there's a command called set trace. There we go. Set trace object true or false. So I'm going to use that in a script on the checkbox here. Change the properties. Scripting. When this checkbox updates, I would like it to do set trace for B, that point, to be the same as the checkbox. So let's see, so if C is ticked, it's going to set trace to B to be true, and if it's unticked, it's going to set trace B to be false. And I think that will turn the trace on and off as well. Let's let this. Oh, I probably need something to animate A as well. Now I'm thinking about it. Let's do another checkbox, and this is again I can't do with a click. I'm going to have to do the scripting commands. Let's say object properties on update start animation A, and this is a checkbox called D. So that should do it. We should now have tick boxes that animate, yay, and another tick box which traces B, yes or no. Let's see. Let's wait till it comes back on the screen. B is currently tracing, and now it's not. Now it is. Now it's not. Okay. And we could have another button to let's have a button to clear the screen. So let's just make a button. And this automatically goes into scripting mode. Clear traces. And the easiest way to do this, you could update the construction. There's a command for that. But if you just zoom in a factor of 1, it's not going to change the screen, but it is going to update it. And that's the easiest way, I think, to clear the traces. Let's just check that that's all working. When B comes back on the screen, it will be tracing. Let's turn it off, and now let's clear it. There we go. So those are the functional bits of Geogebra to make quite quickly, and that maybe is less valuable to do on screen, but building the thing in front of them might be good. It's probably worth mentioning too that for aesthetic points of view, if you right drag a checkbox, you can move it around, and if you've got a grid on and you've got snap to grid happening, which is this magnet control here, it's automatically at the moment, then you can lock these to grid points while that grid is there, and even then when you move the graph around, they aren't going to move, and they're like nicely justified. So now when I drag them back, they don't move, but they have been nicely justified. That's one easy way of making checkboxes look a little tidier. But now we've got them, let's update the original function. I'm going to turn the gradient function off because I don't want to give any spoilers. I'm going to turn the tangent off, and I'm just going to change the original function. Hey, if we're on the task of customizing this, let's do full input box, right? Let's have an input box, which means you can type something onto the screen, which will change the function. How does an input box work? You click on the screen, it says, what's the caption? And I'm going to call it the function f of x. And I would like it to link to the function f of x. And you can see it's called a function, and it's written in the function that's up here. And when I change it, let's put x cubed in there, shall we? This is a neat way of updating, and that way you could possibly hide the algebra view and still have a way of changing objects on the screen. And if you're going to make a finished file ready for preparation, that would be the way to do it. So let's put in a new function. Let's put in sin x. And lo and behold, we have the sin x function. I need to zoom out a bit. Geogebra will plot sine in radians because it's a mathematical piece of software. We can make it plot in degrees, more on that in a moment. Let's just run with radians for now. Let's just check we can animate, yay, and we can show the tangent, yay. This is the tangent of sine at any point. So what is the gradient function of sine? Well, if I just show the gradient point and function, I can show B tracing. I really would like to have had a separate tick box for B, so I don't show the function straight away, but let's just do it now. There it is, and let's trace it. There's B tracing out the gradient function of sine x, which is cosine x, as long as you're in radians. While we're on this, let's quickly demonstrate what happens if you did plot sine of x in degrees. Let's turn off the gradient function and turn off B, clear the traces with all my things. I'll leave it animating. Let's do sine of x. And to put degrees in Geogebra, just use Alt-O, which puts the little degrees. That's actually code in Geogebra for multiplied by 180 over pi. So that's just a number in there, and that's the conversion factor. So degrees symbol is actually a number. It's quite neat. If I plot this, it looks horrendous, but that's because my scale. So shift drag on the scale, and this will start to look like a sine wave in degrees. Nice. Had a little glitch there. And there we go. That's in degrees now. But if I look at the gradient function, and this is why calculus on trigonometry does not work unless you're working in radians, because the gradient function of sine x is not cosine x in degrees. It is a very squashed cosine x, and if you want to see actually what it is, then you can see it is cosine x in terms of its period, but not in terms of its amplitude. It's not tall enough. And this is one other reason why radians are really helpful. I remember when I first realized this, it was like a double barrel shotgun. Radians are great for sector areas and circumferences, but they're also the only way you can get calculus to work on trig in a sensible, neat manner. And it just works when you make 2 pi instead of 360 things around a circle. I'll do another video sometime on making a nice file to demonstrate that. But for now, we've built a gradient function, we've done some aesthetics with it, and this is a really useful tool. At least part of it, I think, is really nice to build in front of a class. The last thing I'm going to do in this video is discuss how you could build it and do it from first principles. So I've got a clean slate back now to a new Geogebra window, and I want to talk about building what we just built, but from first principles. And the only real difference here is I want to build a tangent without talking about the tangent tool, which is kind of cheating for us. And this will be appropriate for a class who are studying differentiation from first principles. How do you know what a tangent to a curve actually is in a neat way? And this is where the idea of limits that can define differentiation come from. So let's build a function again. I'm going to build the same function, f of x equals x squared, brackets 1 minus x, add 1, just give it a bit of space. Let's zoom in and have a look at this function a bit better. There we go. So there's a nice function. I'm going to put a point on it exactly like before and realize I don't know how to draw a tangent to this curve. But what I do know how to draw is an approximation to a tangent of this curve. And to do that, I'm going to create a slider, which I'm going to call h for reasons which you may be familiar with. I'm not going to let it become 0. I'm going to let it become very small and go up to, I don't know, about 1. And let it change in small amounts. The thing is, this h is, I don't know why we call it h when it's actually not really a height, but a width. Anyway, imagine whatever a as a point is, I would like to have another point a little bit further on. And I'm going to say that a little bit further on, I'd like to be the distance h. So let's build that point. I'm just going to type it in. When you get you think, oh, there's no tool for a point a bit further on. You just type it in to Geogebra. And this is why I'm a big fan of learning how to use the input box here. So build a point which has the same x coordinate as a plus h. And then I want it to be on the function. So I need to do f of x of a plus h, close brackets. And actually understanding that is a big part of understanding how functions work. And now we've got a really nice demonstration that as a moves around, b moves around a little bit ahead. In fact, the amount it's ahead is this slider here. So you can bring it in close or you can bring it further away. And the reason I've done that is if I've got a point which is quite close to a, it's not that close yet, but if it is there, I can build a line between them. They quite often call this a chord, although I think the chord would just be the bit between a and b. And I want the whole line here, not just a line segment. That is not a tangent to the curve. You can see it's not a tangent to the curve there. It's crossing the curve. But as h gets small, or as b gets closer to a, then it actually gets very close to the tangent to the curve. And when h is 0, it doesn't work at all because there would be no line to draw. But if you don't let h actually reach 0, then maybe I was wrong earlier. Maybe I should let h be 0 for the sake of the pedagogy here. When h is small, it's a good approximation, but when it's 0, the line disappears, and it disappears in Geogebra because when 2 points are the same, you can't draw a line through them, or you can draw infinitely many lines, so the line is not defined. But if h is very tiny, maybe I should turn on turn up the rounding so we can actually see how tiny h is. If h is tiny, this is a pretty good approximation to a tangent to the curve. At this point, you could wheel out the tangent command, there it is, and show how close it gets. But we've already got a way of defining the tangent to a curve as a point. And what we could do then is maybe draw the triangle which determines the tangent, the gradient of that thing. So let's do a neat way of doing that. I'm actually going to do this just with the input bar. The corner of the triangle will have the same x coordinate as b, equivalently x of a plus h, and its y coordinate will be the same as that of a. So let's do y of a, and there's my point, and I can just use some line segments to join these together. I probably don't want the labels on there, so I'm just going to select them and turn the label off. And now I've got a little triangle which, as h gets small, is approximating the gradient, and I could even label things on it, right? I could say the vertical line is, well, that's the complicated one. Let's get the horizontal line is h, so let's actually just put a label on the screen. Now, labels are a bit annoying. I'm going to do this one way. When you choose text, you can just click on the screen and you can enter some text, and it'll turn up on the screen there. And you can drag it around. Great. But actually, you wanted to track around with this, so I'm gonna actually attach it to a point, and you can see the tool says select position or an existing point. So I'm going to create a point called the midpoint of the segment I just made, which I think is I. There it is. It's called D, and I'm going to attach some text to that point. And let's call this H. And actually, if I wanted to look like math formula, I can turn on the LaTeX formula. It looks like H. And now I can drag this around a bit, but it's attached to D. So I can actually leave it there. And maybe I'll hide D now. And as A moves around, I'm hoping H moves with it. That's pleasing. Now, it's still faffy to get the presentation right. Geogebra is not entirely an aesthetic thing in original purpose, but you can make it look nice. And actually, the important one up here is let's get the midpoint of that one So we've got a place to put it. I think that's called J, that one. And then I want some text at E or close to E. And this is the important point. What is the difference in that? Well, it's the value, the y value of B, which we said was f of x plus h, subtract the y value of A, which is f of x. And I want this to look like proper mathematics, so turn on LaTeX. And there we go. That is a description of there. Let's hide E. And the gradient, therefore, let's use the text in full here, is going to be, therefore, grad. If I'm going to write proper text on Geogebra, I might as well talk about it here. I'll turn on LaTeX. But if I do want some text still, I might just write full-on LaTeX commands, /text, open some curly braces. And now when I type text, it looks normal. It looks actually quite serifed and neat. So let's do that. Grad. Oh, just deleted my bit. /text, open gradient equals. And then if I end the text, I'm back into mathematical LaTeX, and it's going to be, I'm going to use the frac command. I want the bit on the top to be f of x plus h minus f of x. And on the bottom, I want h. And we have a nice looking formula for that. And what's great about this diagram, it looks like it's come out of a textbook. Perhaps I can put that up there, but it moves. And so I drag A around, you can see it's compensating. And if I make h small, this goes down. So what we could have done is built this earlier. Oh, that's moving around up there. I don't like that moving around. This quite often happens when you make text. Right click on it and click absolute position on screen, and now when you drag, the text doesn't move. So what we could have done earlier is, instead of using the tangent command, we could have built this whole construction of a chord or a line segment that comes from a chord and let h tend towards 0, which is kind of the whole point of differentiation. And it's nice to have this diagram that moves but captures the classic derivation of what the gradient is. And actually, this is where we define gradient to be the limit of that calculation when h tends to 0. So I shouldn't have said equals. What I should, let's go and edit this. The gradient of tangent is approximately, and I wonder if I can do approx. I don't know if it's approx. Yes, it is. So the gradient of the tangent is approximately that. Should we write the proper thing? I'm going to write the proper thing here. So the gradient definition equals, and let's turn it into LaTeX. You'll figure out you want LaTeX if you start typing LaTeX commands. You can see it's already figured that out. The gradient definition is, now how do we do limit? Do lim? Yeah. Subscript as h goes to 0. I need an arrow. What's the arrow? They're all in here somewhere. Symbols. And this is when knowing your LaTeX. I normally end up spending a long time on Google. That's what it is. I feel like there's a better way to do that, but I can't remember the command. As h goes to 0, close that. Limit as h goes to 0 of, and let's do the frac again. F of x plus h minus f of x. Why is it? It's gone strange. I'm still in text mode, so let's just end the text bit there. And the bottom of the fraction is h. And that is the definition. Wait, do we want brackets around all this? We can do left bracket. Does that work? I don't know if it does. It should work in there we go. Oh, it's done it. There we go. I like that. It's important to recognize that Geogebra is a mathematical piece of software, and it's relief, therefore, that it can write mathematical notation in LaTeX quite neatly. But if you have no idea what I've just been talking about with LaTeX, and you think I've been mispronouncing it, then go and look it up. It's a way of mathematical typesetting thing, and at least Geogebra will do it. I feel like I misspelled gradient there, but I haven't. I need to go and look up what the LaTeX command for an arrow is to get that right next time, but I hope that's been a useful introduction to a simple way to build a file for your students when you're talking about gradient functions, and building it yourself in front of them, I think, has some merit. Consider whether you want to do that and whether you want to let them loose and build it themselves. I guarantee if you give them the option, some who are getting into it will enjoy this. We should talk about integration in another video, but that's next time. So hope you've enjoyed this, and I'll see you next time.